Okay, so with this one, this is the difference here is this is even ground with angle. So the distinction, the ones that we did on Monday were horizontal launch, uneven ground. I mean, it makes sense, so it's going off. The one we did yesterday was angled launch, uneven ground, meaning that it could have gone down, or like the softball one could have gone up to there. This one is even ground with angle. Basically what that means here is that our pictures are going to look, we'll answer this question after we do the problem. Our pictures are going to all look something like that. It's going to be launched from the ground, it's going to follow a parabolic curve, and it's going to land at the exact same height at where it started. We'll do number 2 first. Jack be nimble, Jack be quick. Jack jumped over the candlestick, the velocity 5 meters per second, an angle 30 degrees of the horizontal. That's a physics version of a story there. We're asked also different stuff here as well. So what is Jack's max height? Now that's a comfortable clue there about how we're going to go about finding that. And then once just an extra extension, once we find the max height, then we just ask ourselves, did Jack burn his feet? If the candle is this high, that's basically if this number is higher than 0.25, he jumped over it. If this number is less than 0.25, he did not clear it. So that's not a normal question. I'm just having you assess what's looking. Then we're going to find what is called the hang time. And I'm specifically calling this hang time, although we could have called the time that we found for the object's hang time, how long it hangs in the air. But I'm trying to use this specifically for these problems because of this idea of the time up and the time down. We'll go over that in just a second. And then the last one, what is the horizontal range of Jack? And horizontal range is just how far horizontally does he move. Basically, what is delta x? So we're having to figure out max height. We're having to figure out the time, the total time that he's in the air, and then how far he moves horizontally. So I'll draw my picture over here. And once again, you have to kind of open. You may say, hey, I have an idea how to solve this. This is different, and this is it's not necessarily difficult. It's just different. We've gotten really used to this. So if this is the arc, basically, that Jack makes in the air, how we are actually, let's go ahead and write out our x and y's. And we'll see for these problems that creating this table, we can do it, isn't necessarily the only way that we're going to solve this problem. So x and y, so Vx, delta x, t. Let me refocus that. Okay, if we're looking at our problem here, we're not really given much information. So this 0.25 meters is not delta y. That's just, we're just going to compare Jack's max height to that. Our information we're given is that the speed is 5 meters per second and the angle is 30 degrees. So we can use our cosine and sine to figure out what Vx and Viy are. So Vx is 5 cosine of 30, and Viy is 5 sine of 30. Have this solved already. 5 cosine of 30 is approximately 4.33 meters per second. And 5 sine of 30 comes out to 2.5. So we plug that into our table here. We're going to come to a realization that the typical way that we solve these problems is not the way we solve them here. We don't have enough in the x direction. We only have one equation, 2 unknowns. and we don't have enough information in the y direction. Now, I've always said, hey, you're always going to have enough in one direction or the other. We need to think about this a little bit differently here. Now, some of you could say there is a way to solve this where delta y would technically be what here? Yeah, delta y would be 0, but you can realize how that might be confusing if we're trying to find the max height, but yet we're trying to find the max height at this point, but we're using delta y over here. So I'm going to avoid doing that. Instead, we're going to go back to the strategy of just looking at the first part of the problem here. And if I were to draw the first part of the problem completely in the y direction, it's just doing what? If in the y direction, in the first part of the problem, what's it doing? It's just going up to its max height. Okay, so I like to kind of draw a problem sort of like this, where I'm using this arrow here to help me list my variables. Not that this isn't necessarily helpful. I just find that if you think about it in terms of drawing another diagram here, where we know VIY, that is 2.5. We know gravity. Okay. We're trying to find the max height, and that tells us what? If we're only looking at the first part here, it tells me what about that in the y direction? Yep, VFY is 0. Yep, I know a lot of you have that. So VFY is 0. Realize that we couldn't say, one of the difficulties in using delta y is 0 is that we don't know what the final velocity would be at that point, and it doesn't really help us here. But recognizing that final velocity is 0 there, this information is enough to not only find delta y, but also find what we call the time, and it's the time up. It's not the total time, it's just the time up. So we're going to use VFY, G, and VIY to first solve for delta y. And if you refer to the equations, I know they're written up kind of small there, but there's an equation over there that doesn't have time that will allow you to solve for delta y. And it is the fourth equation, the one on the bottom. I know it's kind of written kind of small there. It's VFY squared equals VIY squared plus 2G delta y. We're not solving for final velocity here. We already know the final velocity when it reaches max height is 0, so we're instead going to use that equation to solve for delta y. Where we know that this is 0 because we're just defining the first part of the problem, because max height has nothing to do with it falling back down to the ground. Initial velocity is 2.5. We know gravity. So we're trying to find what is that delta y right there. When you get an answer, we have an answer for that one? 0.32, yep. 0.32 meters. Okay. So that's A. B is just saying, hey, is that higher than 0.25? Yes, he does clear it. Or sorry, so it says, did Jack burn his feet? No, he didn't burn his feet. You could just justify that as this number is bigger than 0.25. It's just assessing something there, not part of the usual problem. So 0.32 meters, not bad. I mean, realize he's not jumping up; he's jumping to the side, or up at an angle. So 0.32 meters is not bad. Okay, now we get to, so basically we're at part C. What is the hang time, the time up plus the time down? Here's the thing about launching from one place and landing at the same exact height. The time up is equal to the time down. I mean, if in the y direction you're just tossing something up and tossing something down, the same gravity slowing it down as it goes up is the same gravity speeding it up as it goes down. Okay, that is only the case with these problems. Okay. If Mario is jumping down from a higher height, we can't say that the time up is the same as all the way down. we also can't say that the time up here is the same as that. This is only for this case here, where you have this even ground. So we are going to use this information here to solve for time, or the time up. So although we're using the fourth equation, and in this case you can use the second equation, I wouldn't call this the 4-2 strat. We just happen to be using these equations. We're not having to do this because of not using the quadratic, but we can use the second equation here to solve for the time. And try to get in the habit of writing time up there when you're dealing with these problems here. I am on this worksheet on the test. I do put this here to remind you that you are finding the time up and basically doing what with that once we find it. How do you find the total once we find the time up? What? Yep, you just double it. Yeah, so 0 equals 2.5 plus negative 9.81 time up. If we round out to 2 decimal places, it comes out to 0.25 approximately there seconds. But that's not what it's asking for. Once again, this strategy we're using, I'm going to repeat it over and over and over. Only for these type of problems are you going to do this, because if the ground is flat, then the time up is equal to the time down. So to find the total, we do this times 2 to find the total, the actual time. So I would say that the biggest way of identifying what you're doing here is to draw that picture, and then even draw this picture where you have this box here, because the 0.25 is this part of the arc. It's that part of the arc, and we need to figure out the whole entire arc. So the total time is 0.5 seconds. That is the hang time. And now all we have to figure out is how far it goes horizontally. We know the velocity in the x direction. We now know the total time that it moves horizontally. So we can use our equation to solve for delta x. So 4.33 equals delta x divided by 0.5. Once again, this there. And it's about 2.17 meters, give or take. Now, if we had used 0.25 seconds, what distance would we actually find? Yeah, we would only find the distance it takes to this point right there. So if we go over where all this kind of came from and why we're choosing to solve it this way, well, our normal filling out of stuff here is sort of incomplete. In order to find the max height, we have to use the time up. So I just to kind of help the time up here. But the thing is, in this problem, the time up is not equal to the total time. That's where there's a disjunction there. So realizing instead, if we set it up like this and just concentrate on the first part, because at that point we can say definitively the final velocity is 0, which gives us enough variables. We know the initial. We can solve for delta y, which we did. We can also solve for the time, but realizing that is only the half the time, we double that times 2, we plug it into there. Every single problem is exactly like this. It's the same exact process. So, yes, is it different? Yes. Are you going to have to, kind of train yourself to when to recognize what type of problem you're being given here? I said as a passing out papers, the really unfortunate thing is I see people that like ace and they're just totally can totally understand those problems over there, but when they see this lesson, they're like, oh, I need to now change how I did all those problems and do them like this. And I'm like, no. So that is why I separate these problems apart from each other. Let's go and talk. Actually, we're going to talk about some conceptual here, and I answer this question. I'll do some notes in the back that'll be help for you. So it says, you may notice that I'm not asking you what the final velocity of these objects are when they land back down on the ground. If you think intuitively, if you take off and land from the same height, how does the initial speed, not the direction, how does the initial speed relate from the initial to the final? So like if this is 5 meters per second here, how fast is it going to hit the ground on this side? Let's think instead of an arc, let's just say I toss an object up at 5 meters per second. How fast is it going to be going when it hits my hand again? 5 meters per second. That's exactly what's going to happen here, okay? That's not the case if I threw it up and then try to catch it up here, or I threw it like that and catch it down here. Oops. But if they are the same height, the speed that it has, not the direction. The direction obviously is going to be different, but the speed is going to be the same there and there. So you don't have to calculate the magnitude direction, or at least the magnitude, because we already know what that is. Let's now move. So I said speed is the same. Let's now move to the other side here and talk about this last. We'll put some notes here. What you're doing for number 3 and 4, if you actually look at 3 and 4, they seemingly are the exact same problem, except what is the difference here? What's the difference between 3 and 4? The angle. And you say, well, that kind of just seems repetitive. Why in the world are we doing this? Once you solve those two, it is going to ask you a question down here and say, does number 3C, which is what is the horizontal range of the cannonball, does number 3C and number 4C, basically the horizontal range of the cannonball, does that confirm, within rounding, that complementary angles produce the same horizontal range? Complementary angles add up to 90, supplementary 180. So the complementary angles 90 degrees. You should see that that is the case. So if you have any two angles, as long as it's the same speed, if the angles add up to be 90 degrees, they will always go the same distance. They won't have the same hang time, but they'll always be the same distance, and I'll show you here sort of where that comes from. Before we do that, though, the optimal angle for distance, so for max range, if you want the furthest range, and we're assuming there's no air resistance, it changes a little bit if there's air resistance, a little bit, is 45 degrees. Because 45 degrees is its own complementary angle. 45 plus 45 is 90. Okay, so that is the best of both, and you'll see this in a second here. Let's look at kind of conceptually here at 10 meters per second at 15 degrees, which is number 4, and we're not going to solve it, but 10 meters per second at 75 degrees. Those two add up to 90. Maybe. Let's kind of conceptually try to understand why these will have the same distance here. I'm going to use two different colors here to try to help that. Let's have the higher angle here be green. I know you can't color. And we'll have the lower angle be red. If we imagine the green, so we start here. We start there. The green one is going to have a much higher angle, so it's going to go a very, very, very high arc and then come back down again. Okay, there's the green one. That's the 75 degrees. And then we have the 15 degrees, which is this lower angle. And although, I guess, first question, which arc is going to be, which path is going to be in the air longer? Which one is going to have a longer hang time, the green or the red? Green. It makes sense that the green is because, I mean, it's going up. It takes longer to go up and longer to come down. And this one is going to have the same. And so let's kind of have an explanation of why that is the case here. It will always work out that those will have the same range. Let's do this real quick. I'll just figure out the x. I just want to figure out the x because this whole thing has to do with the x direction. The whole reasoning behind this has to do with the x direction. Let's see here. 10 cosine 15 is 9.66. and 10 sine of 75, or not sine, sorry, 10 cosine 75, we're just finding out the x components, is 2.59. The reason why we're only looking at the x direction is that the time is based on what's happening in the y. And we can, hopefully we can see here that the time for 75 is going to be very, very big compared to the time for the red. However, how is it made up here? If we have our equation here, Vx equals delta x over t, where delta x equals Vx times t. If the time of the green one is so much more than the red, then how is it that they have the same distance? Something is bigger for the red. Henry?
Yes, velocity is much bigger.
Yes, the component of the velocity is far more in the horizontal direction than it is here. Although it's not moving for a very long time because it's not going up. If we look at the y component, we see that it would be really small. It's moving fast. So the short amount of time it's in the air, it's moving really fast horizontally. Whereas the green one, it's in the air for a substantially longer amount of time, but how fast it's actually moving sideways is a lot longer. So in this case here, we have a big Vx, and in this one, we have a small Vx. And it ends up that those two things, those factors, end up canceling each other out, and the delta x is going to be the same. So we say complementary angles will always have same range or same distance. Just one's going to be in the air longer than another one. Okay, so that is a conceptual thing right there. And what you're doing for 3 and 4 is that you're sort of mathematically proving this. You're solving the problem for each of the parts, and the horizontal range you get for 3 and 4 within rounding, it is a teeny bit different because if you're rounding to 2 decimal places, some of the rounding gets off, but you should see that it should produce the same exact range. So 3 and 4, yes, you're doing very similar problems, and you're comparing both of those. So if we look down here, it says, if so, what angles would produce the same range as these angles? Let me be a caring teacher here and say that I'm totally okay if you take these numbers and you subtract them from 90 in a calculator. I've seen too many times people down in their luck say like 55 here, or they say like 75. So just put it in your calculator. Okay. I saw an article where a teacher was saying that, in the heat of battle of a test, people's brains sometimes turn to mush, and then they just put crazy answers down there. So 90 minus 30, that should be 60. 90 minus 25 should be 65. And 90 minus 5 should be 85. Here's another rationale. Here's another rationale why they're going to have the same distance. If you were to fire up an object at exactly 90 degrees, and then you were to fire another object at exactly 0 degrees, how far is the 90 degree? How far is the one that's going straight up and down? How far is that moving sideways? None. It's not moving sideways at all. And if you have an object that is on the ground and you kick it sideways, it's not in the air for any amount of time. It didn't move. So 90 degrees plus 0 equals 90. Even these complementary angles show that it's not going to move. It's going to have the same distance, which is nothing. That's kind of wraps up sort of the conceptual part of that right there. Obviously, we have time. We have a little bit of time. You can work on it now. But sort of I built in for Friday to be able to work on this. Now that with this conception, there's some problems up here from the book, the angled even ground, which we just did. These conceptual ones are related to this kind of idea right here, that the higher the angle, the longer it will be in the air. So Friday, that's why it's good to get your runs in on Thursday. I'll get the, I don't have the solutions to these yet. I'll get them.